Energy density, part 3. A discussion of hydraulics, Venturi tubes, and fluid flow. Here is an illustration from your text. This illustration just starts our discussion on hydraulics. In short, the idea of hydraulics is to have ordinary forces, such as from the weight of a person, create extraordinary forces, a force to lift up, to balance the weight of an elephant. Well, right below the platform that the person and the elephant are standing on is a pressure A and pressure B. Pressure A connects the platform to the fluid, and pressure B connects the platform underneath the elephant to the fluid. What do we know about pressure A and pressure B? That they are equal, because they're at the same level in the fluid. So the pressure at the same level in the fluid must be the same. So PA is equal to BP, therefore the pressure right beneath the man and the pressure right beneath the platform the elephant is standing on are the same. They create the same pressure. These different weights, these different forces are creating the same pressure. How could these different forces create the same pressure? Relationship of pressure is force per area, or F per A. Pressure is also an energy per volume, or an energy density, joules per meters cubed. The units for force per area, newtons per meter squared. That's okay, because a joule is a newton per meter, and we know work is force times distance, which is newtons times meter, force times distance. So joule per meter cubed equals newtons per meter divided by meter cubed gives us a newton per meter squared. So joule per meter cubed is the same as a newton per meter squared. Okay, enough on the units. So pressure is a force per area. So if the pressure under the man and the pressure on the elephant are the same for these different forces, it must mean then that the lesser force of the man creating the same pressure underneath the elephant, who has the greater force, the greater weight, must be compensated by a lesser area under the man and an equally greater area for the equally greater force for the same pressure under the elephant. So force per area for A is equal to the ratio, the same pressure of force per area per B, which is the weight of A and the weight of B are the forces. Since the pressure is the same, we can equate these two ratios, the ratio of the weights and the ratio of the areas. So knowing the weights, or the ratio of the weights, times it by the area, we can figure out the area of the platform, area A that the man is standing on. Given the information of the weight of A, the weight of the man, and the weight of the elephant, and assuming that the elephant is standing on a 2x2 platform, we know the area, therefore we can create the area A, the area under the man, the area of the platform that the man is standing on. Plugging in our numbers, the weight of the man is 70 times g, the weight of the elephant is the mass of the elephant times g, but the g's cancel. Assuming the elephant standing on a 2x2 platform, then 70 over 1200 times it by 2 squared will be the area of the platform the man is standing on. You can conclude this calculation. And that would be 7 per 30 meters squared. That's the area of the platform the man is standing on. If you want to know the size of the platform in terms of the length of each side to give us a 730 meters squared platform, well, area is length squared. Square of an area, the square root of an area, gives us the length by definition, what it means to be a square root. So length is the square root of 7 per 30, which is approximately 48 centimeters, is the length of the square of the platform the man is standing on. If the platform is a circular platform, a disk, then the 2 can represent the diameter, and we do a similar analysis for the diameter of the platform that the man was standing on. Another example, hydraulics, fluid flow. Here we have a tube that splits into a wider tube, and then the fluid flows into a branching, smaller 2 narrow tubes. Spot 1, 2, 3, and 4 are locations in tube 1, 2, 3, and 4. Well, I represents current. So I1 is equal to I2 is equal to I3 is equal to I4. in this tube. Current is a stuff per time, or a conservation of stuff per time. The amount of current or stuff that flows into tube 1 must be the same amount of stuff that flowed into tube 2, which must be the same amount of stuff as the combination that flows into tube 3 and 4. All the stuff that flowed into 1 must flow into 2. If 1 liter every minute is flowing past tube 1, then 1 liter per every minute is flowing into tube 2. That's what it means to have the same flow rate or current I in tube 1 as tube 2. I'm using the symbol I for flow rate or current. So a liter per minute flows through tube 1, therefore a liter per minute goes into tube 2, and a liter per minute gets split. The current gets split in I3 and I4. Now, relationship for current is area A times velocity. So the area of tube 1 relates to the velocity of tube 1. The bigger area of tube 2, the same product, area times velocity, is current, but I1 is equal to I2. So therefore, area 2 times velocity 2 is the same as area 1 times velocity 1. But area 2, the cross-sectional area of tube 2, is bigger. It's a bigger, wider tube. Therefore, the velocity is less in tube 2. Less velocity doesn't mean less current. It's still, for example, a liter per minute going into tube 2. It's just going in there slower. Less width of that liter is going into tube 2 than in tube 1 to compensate for the greater area. So if you know the currents and the cross-sectional areas, we can figure out the velocity. Now, going in our analysis from 1 to 2, y2 and y1 are roughly the same height. There's no change in gravitational energy because there's no change in height from 1 to 2. Our tubes aren't tall enough or wide enough to have changes of height. And there's no temperature difference between T2 and T1. So there's no thermal energy changes. But the velocity of 2, we already said, is less than the velocity of 1. Tube 2 is wider, so the fluid flows slower in tube 2. So the change in velocity is not 0 from 1 to 2. Therefore, there is a change in kinetic energy for a volume that flows through fast through 1 and slows down through 2. It's going fast through 1 and slowing down. It's losing kinetic energy. Our volume, or liter for instance, is losing, or 1 liter per minute, loses kinetic energy from tube 1 to tube 2. But again, I1 is equal to I2. It's going fast in 1 and slow in 2. V1 is greater than V2. That means the kinetic energy in tube 1 is greater than in 2. So the kinetic energy has been reduced going from 1 to 2. Our fluid is slowing down. We know this. Our indicator, our observable, easier to measure as the cross-sectional area of tube 2 is bigger. Therefore, going from 1 to 2, we've decreased velocity as we increase size. So this fluid is slowing down, decreasing kinetic energy. So it's a loss in kinetic energy per volume going from 1 to 2 as it slows down. There must be an increase of some other form of energy. But we just said there's no increase or change in temperature. There's no increase or change in gravitational energy. There's no increase or change in height. So no thermal energy or gravitational energy is involved. There are no springs or chemical or nuclear energy. So what must balance our energy conservation? What must balance our books? Well, no change in temperature, no change in Y. That must be a change in pressure. Going from 1 to 2, there's a pressure difference. Our pressure increases from 1 to 2 as the fluid slows down. As it loses kinetic energy, it must gain pressure. There's more pressure in tube 2 than in tube 1 as the fluid slows down. Substituting in our formula for kinetic energy, keeping in mind that delta V is equal to V2 minus V1. Going from 1 to 2 is like going from initial to final, so a delta is always final minus initial. Therefore, it's P2, which is greater than P1, since V1 is greater than V2. And our signs work out in our equation. I've just drawn gauges, pressure gauges, on the top of the tubes. The pressure gauge at the top at noon would be 0. As we increase going clockwise from the top or the noon reading on the pressure gauge, we're increasing pressure. We know P2 is greater than P1. Since the velocity is less at 2, the pressure is greater. So going clockwise from our zero pressure, P2 is recorded as greater than P1 in our pressure gauge. That's a pressure gauge. It registers a difference in pressure between the tube, inside the tube, and outside the tube. P in minus P out. P in is greater than P out. P out is the pressure, the ambient pressure, the atmospheric pressure, the surrounding pressure, pressure out of the tube. And since P in is greater than P out, and more so in 2, then pressure 2 is greater than atmospheric pressure. Now similar analysis from 1 to 2. Again, fluid is flowing from 1 to 2. So as our fluid flows from 1 to 2, it's also descending in height. Going from 1 to 2, we're going down in depth, decreasing. The water is falling or moving down, so there's loss in gravitational energy for every volume of fluid. It's got to be increased. As the area is increasing, the velocity is decreasing. So our kinetic energy from 1 to 2 is decreased as we go to a wider tube. So we're losing gravitational energy and we're losing kinetic energy for every volume that flows. Both these forms of energy are decreasing. Both these forms of energy are draining away in these energy tanks. Some other form of energy or another energy tank must increase. Well, again, pressure comes to the rescue. The losses of these forms of energy are equated by a gain of another form of energy. It's not a gain in spring energy or nuclear or chemical or thermal, so it must be a gain in pressure. So P2 is greater than P1 again, because both gravitational energy and kinetic energy for the volumes of fluid flowing have decreased as it falls and slows. So we can substitute in, again, our variables, our relationships, our formulas for gravitational energy and kinetic energy, and equate the greater pressure at 2. So P2 minus P1 equates to the formulas for gravitational energy and kinetic energy. And the signs work out to show greater pressure at 2 than 1. As we decrease the gravitational energy and decrease the height and decrease the kinetic energy. Substituting in some made-up values, let's say 2 atmospheres and 1/2 atmospheres of pressure decrease, of gravitational energy. Let's go back to that. Let's say that we drop by 2 atmospheres of gravitational energy, and we measure a decrease, we calculate a decrease in kinetic energy of 1/2 atmospheres. Well, that adds up, of course, to 3.5 times 10 to the 5th, 3.5 atmospheres of pressure increase of 2 to 1. So the pressure of 1 plus 3.5 is equal to the pressure of 2, made up numbers. Now what if we go from a wide tube to a narrow tube, but the wide tube is higher than the narrow tube? Going from 1 to 2 as our fluid is flowing from wide to narrow, we're again decreasing in height, we're decreasing gravitational energy. So decreasing gravitational energy per every volume of fluid. So our formula is rho g delta y, a decrease in gravitational energy density. It's a negative for the decrease of energy and a negative for the drop in height. So overall a positive number of joules per volume. We're decreasing the tube's cross-sectional area, so increasing the velocity, increasing the kinetic energy. Increasing the kinetic energy for every volume. And the formula for that, well, is the decrease in gravitational energy balanced by the increase in kinetic energy? If so, there'd be no pressure change. The loss of one is the gain of the other. What if the gravitational energy is greater than the decrease in kinetic energy and the increase in kinetic energy? Or the gravitational energy decrease is less than the increase in kinetic energy. If they're not balanced, then pressure has to come into play. But if they are, there is no change in pressure. So if they do balance, then the change in pressure is 0. P1 would be equal to P2 if the loss in gravitational energy is equal to the gain in kinetic energy. So going from wide to narrow tube doesn't necessarily mean there's a pressure change. Going from wide to narrow does not necessarily follow that the pressure is going to drop. That's only if nothing else changes. But if both gravitational energy and kinetic energy change, and in proportion to each other, the pressure does not have to change. Let's say instead the increase in speed, the increase in kinetic energy is greater than the decrease in height energy, the decrease in gravitational energy. If that's the case, then the change in pressure cannot be zero. We must lose more energy. We must have another energy tank, another form of energy decreasing to account for the greater increase in kinetic energy. So the pressure would have to decrease from 1 to 2 to account for the greater gain in kinetic energy. And our equation would reflect a loss in pressure from 1 to 2. And then we'd have energy conservation. What if instead our loss in gravitational energy is greater than an increase in kinetic energy? There's more of a drop in height than there is a gain in speed in a sense. If that's the case, then the pressure would have to increase from 1 to 2. So both kinetic energy and pressure would have to increase to account for the loss of gravitational energy. And then our energy conservation equation would be adjusted to a gain in pressure, so that the pressure in the narrow tube, tube 2, is greater than 1. Again, it's not a general rule that going from wide to narrow we drop pressure. Pressure is simply there to balance the books, if need be. So here P2 would be greater than P1 for this particular example, for this case. These aren't general rules. Now here's a faucet with water falling out of the faucet. In the faucet the pressure is high, but as soon as the water leaves the faucet, the liquid is now at atmospheric pressure. If it wasn't at atmospheric pressure, it would spray everywhere. But as soon as the liquid is outside, exposed to the atmosphere, it quickly becomes atmospheric pressure. It's higher pressure inside the faucet, but once it leaves, it's now atmospheric pressure. So we're dropping in pressure from high to returning to atmospheric pressure. So this drop in pressure has to be equated for by another increase. But we lost height. It's falling. So the drop in pressure and a drop in gravitational energy. Therefore, there must be an increase in kinetic energy. Of course there is. It's falling. It's gaining speed. So it's both falling, losing pressure, and gaining kinetic energy. So it's falling faster and faster. But we know if a fluid gains kinetic energy, it must decrease its cross-sectional area. That's our indicator of an increase in kinetic energy. Therefore, the water falls and gets narrower and narrower as it's gaining speed. When liquid gains speed, the column of liquid gets narrower to reflect the gain in speed. This is why the water going from a faucet gets narrower and narrower, and also why it rotates as it gets narrower and narrower. It's reflecting the gain in kinetic energy or the gain in rotational kinetic energy. Another example of pressure. Here's a cross-section of a wing of an airplane. The velocity above is greater than the velocity below, because the velocity of the air above has to cover more distance in the same time as that below. Therefore, there's an increase in kinetic energy going from bottom to top. Therefore, there's a drop in pressure. Pressure above the wing is low. Pressure beneath the wing is high. This creates a lift. High pressure below, low pressure above. High pressure below and low pressure above, because going from bottom to top, beneath the wing to top, we've gained speed, so we must lose pressure. Gain in kinetic energy and a loss of pressure. Drawn here is a Venturi tube, a tube where water flows from a wide part to a narrow part to another wide part. Going from 1 to 2, we're going from wide to narrow, so we're decreasing cross-sectional area, is increasing velocity, which means we're increasing kinetic energy of volumes of liquid that flow through this Venturi tube from 1 to 2. Therefore, there's no change in height, no significant changes in height. These tubes are narrow, not of great depth. So there's no change in gravitational energy, or spring energy, or nuclear or chemical. Therefore, again, pressure is here to balance the books. Going from 1 to 2, we increase kinetic energy, so we dropped in pressure. So P2 must be less than P1. If P2 is less than P1, the pressure beneath 1 is greater. It presses up a higher column, a taller column of liquid, and P2 presses up a column of liquid, a stagnant, non-moving column of liquid above P2 that's of less of a height, reflecting the less pressure at P2 than P1. Again, the water is not moving, so going from P1 to P4 at the top of that column, we're simply pressing up. The greater pressure is lifting up or increasing gravitational energy, going from 1 to 4, as we started with the barometer. So there's a change in pressure going from 1 to 4. It's accounted for by the increase in gravitational energy. The height of that column reflects the change in pressure going from the bottom of the column to the top of the column. It's simply a barometer. It's a pressure gauge for tube 1. Going from tube, and looking at the tube 2, going from 2 to 4, which is also an atmospheric pressure. The change in pressure from 2 to 4 is again related to the gravitational energy, rho gh from 2 to 4. Except the height of column 2 is less than the height on top of tube 1, because there's less pressure in tube 2. Measuring the heights of those columns directly relates to the pressure at tube 2. These are gauge pressures, these columns. Difference in pressures are gauging the pressure in tube 1 and tube 2. Going from 2 to 3, we're increasing our cross-sectional area, so the water is slowing down, the fluid is slowing, so it's a loss in kinetic energy and a gain in pressure. Therefore, P3 is greater than P2, and so the tube rises from between 2 and 3. Our gauge pressure shows us the greater pressure at 3. But the pressure at 3 is not as great as the pressure at 1, even if the tubes are the same size, even if tube 1 and tube 3 are the same size. The reason is we didn't account for all the energy systems. As the liquid is flowing from wide to narrow to wide, lifting up different columns of fluid, it's also rubbing or dragging against the sides of the tubes. This is an increase in thermal energy along the way. So we have both an increase in thermal energy and an increase in pressure going from 2 to 3, going from 1 to 3. Therefore, the height of column 1 is the greatest, height of column 3 is next, and the smallest is height of 2, reflecting the differences in pressure between 1, 3, and 2.